Welcome back to another explainer. Let's just jump right in today because we are taking a massive, truly fascinating leap. We're unpacking Lesson 11 of the Clinical Cognition course, and we're tackling a question that is absolutely vital for the future of medicine. How does medical reasoning actually scale up? I mean, really think about it for a second. What happens when a diagnosis is just simply too big, or a patient's history is too incredibly complex for one single mind to hold? For a long time, pop culture and honestly, even medical training, they've both focused really heavily on the solo doctor, right? The brilliant lone diagnostician cracking the case. But the reality of modern healthcare, it isn't a lone genius. It's a massive, buzzing, highly complex hospital network. So the real question is, how does an entire organization think? To figure that out, here's our roadmap for today. We'll start with 1, the core cognitive engine. Then 2, the limits of the single agent. 3, multi-agent workflows. 4, mastering the structured handoff. 5, distributed differentials. And finally, 6, systems-level safety. Okay, let's dive into this. Section 1, the core cognitive engine, or as we like to call it, the solo detective. To truly understand the macro-level operations of a whole hospital, we've first got to quickly ground ourselves back in the micro-level. We've seen this core loop of clinical cognition in action in the earlier lessons. It's step 1, observation. Step 2, differential building, where you take raw findings and create a probability-weighted list of possible diagnoses. And step 3, bias auditing. This right here is our foundational cognitive engine. You can kind of think of this single clinician as a single, highly capable processor in a much larger computer network. They are brilliant, for sure. They're highly trained, but ultimately, their processing power is bounded. So what happens then? That brings us to section 2, the limits of the single agent. And what goes wrong when that core engine just isn't enough? Imagine panning the camera out from that one single processor to a sprawling network of, say, thousands of them. We have to look at the friction that inevitably pops up when a solo doctor gets completely overloaded by sheer volume, time constraints, and complexity. Single-agent reasoning is highly perceptive, absolutely, but it's fundamentally fragile at scale. Why? Because that brilliant thought process is largely invisible. It lives entirely inside their head. If they clock out, well, the reasoning clocks out right along with them. Now compare that to multi-agent workflows. This operates way more like an intelligence agency. It has to be robust across different teams, different shifts, and it relies heavily on structured data protocols so that the actual thinking survives the transition between people. Which leads us perfectly into section 3, multi-agent workflows, essentially expanding the mind. Now, what's really interesting here is how this solves the problem of cognitive collapse in a super busy healthcare setting. The course index captures this perfectly. Quote, extending single-agent reasoning to multi-agent organization-level workflows. We are no longer just asking, how does the doctor think? We are zooming way out and asking, how does the hospital think? We are taking that delicate internal reasoning trace and turning it into a tangible operational asset that the entire organization can use. So, to actually make that happen, Lesson 11 outlines 3 specific organizational mechanisms to prevent system failure when we scale up. We've got structured handoffs, distributed differentials, and systems-level root cause analysis. These are literally the operational tools that allow multiple minds to act as one single coherent diagnostic engine without dropping the ball. Let's break these down one by one. Starting with Section 4, Mastering the Structured Handoff, which is basically our data transfer protocol. I really like to think of this from an engineering perspective. A structured handoff is a formalized method of relaying a clinical reasoning trace, and notice I said reasoning trace, not just the final conclusion, safely to the next clinician or team. Think about playing a high-stakes game of telephone. If I end my shift and just hand you a piece of paper with a diagnosis scrawled on it, you have no idea why I arrived there. You don't know what alternatives I considered and discarded. But if I use a structured protocol to transfer my actual reasoning trace, we completely prevent that distortion between shifts. The intelligence survives the transfer completely intact. Moving right along to Section 5, Distributed Differentials, all about collaborative problem solving. So, if handoffs are mostly about time, passing vital info safely from shift to shift, then this concept is all about space. How do we share diagnostic possibilities across entirely different specialties and departments in the exact same building at the exact same time? A distributed differential takes that core process of differential building we saw back in Lesson 3, and it scales it massively. It's the multi-agent process of building, sharing, and stress testing diagnostic probabilities across an entire organization. Just imagine an ER doctor, a radiologist, and a lab technician all interacting with and tweaking the exact same diagnostic probability list in real time based on incoming data. It's collaborative problem solving at a true operational scale. But of course, things go wrong. Let's look at Section 6, Systems Level Safety, and what happens when the network fails. Because look, even the best networks sometimes drop packets, right? How do we investigate failures and errors when there isn't just one person making a decision, but an entire network of agents working together? A single record failure usually involves an individual cognitive bias, or maybe a specific error made by one doctor at the exact moment of commitment. But a system-level failure, that is an entirely different beast. That's a breakdown in our handoffs. That's multi-agent communication errors. It's not about one single processor crashing. It's about the entire network routing protocol failing to deliver the message. And this brilliantly illustrates how our approach to safety has to evolve as we scale. Under an individual view, root cause analysis focuses on the solo decision and targets a single moment of commitment. But when you zoom out to that systems level view, the focus shifts entirely to handoff distortion and workflow collapse. The target is now multi-agent operations. When an error happens here, we aren't just auditing a doctor. We are literally auditing the organization's entire operating system. Which leaves us with this incredibly powerful takeaway summarizing everything we've talked about in Lesson 11. Clinical wisdom isn't just about the solo doctor. It's about the entire system they operate within. To build truly robust, reliable healthcare, we have to engineer the workflows, the data transfers, and the safety nets to support the collective intelligence of the whole organization. The brilliant solo detective is great, but the well-oiled intelligence agency? That is what saves more lives at scale. So I want to leave you with this provocative question to ponder. Whether you're in a clinical setting, building health tech, or managing complex operations anywhere, really, how traceable is the reasoning in your system? When the shift ends, does the intelligence just evaporate, or is it safely handed off to the next agent? Thank you so much for joining me on this explainer. I really hope this sparked some new ways to think about systems, and I'll catch you next time as we continue unpacking the fascinating first principles of cognition.